All right. What we're going to do now is look a little at the mathematical and actually, as a result, also the physical properties of these two new tensors. Okay, so let's look at mathematical properties of C and of E. Okay, first of all, recall that C is F transpose F. Okay, what does this imply for C transpose? Okay, what this implies is that C transpose, now, if C is the product of two tensors on the right-hand side, the transpose of a product is the product of the transposes, but in the reversed order, right? Well, that really makes no difference because it means that we have to write this tensor first, transpose, followed by this tensor, transpose, but that just gives us back F transpose F, which is equal to C, right? So C transpose is equal to C, which means it is symmetric. Okay? One more thing. What is the effect of doing something like this? Epsilon m dot C epsilon m. We've seen that this can essentially be written as, in fact, this is how we originally constructed it, right? We constructed it as F acting on epsilon m dotted with, again, F acting on epsilon m, and as I did before, I've simply pulled out epsilon because it's a scalar. But what do we know about the term on the very right? It is a square, right? Because it's the magnitude of a vector, right? It's the magnitude of a vector square. And therefore, this term is greater than or equal to 0, right? In fact, this term is greater than or equal to 0, and in fact, epsilon m dot C epsilon m is equal to 0 if and only if, and that is written as that symbol IFF, right? Epsilon m dot C epsilon m is equal to 0 if and only if, what? If and only if epsilon itself equals 0, right? But if epsilon itself is equal to 0, it means that the original vector that we were testing here was of 0 magnitude anyway. That's the only situation under which this product would turn out to be 0, this quadratic product would turn out to be 0. There's a special name for tensors of this type, for tensors C of this type. Can you recall what that is? We've essentially defined a particular property for C. By definition, C is also positive definite. Okay, and the last two lines are essentially the definition of a positive definite tensor. Okay? One more thing. If we now consider the determinant of C, we observe that it is the determinant of F transpose F, which is the determinant of F the whole square, because the determinant of the transpose of a tensor is the same as the determinant of the original tensor. Okay? But we already knew that determinant of F has to be greater than 0 from our condition of local impenetrability of matter. Okay? It follows therefore that the determinant of C is also greater than 0. Okay? One last thing. Let's consider what happens with E. Now, we've decided to define E as 1/2 C minus the isotropic tensor. We just discovered that C is symmetric. The isotropic tensor is also symmetric, right? As a result, we have E equals E transpose. It too is symmetric. Okay? Does E have to be positive definite? Does E turn out to be positive definite? Think about it. Is there any reason for E to be positive definite just as C is? Well, let's find out. In order to check if a tensor is positive definite, all we have to do is have it act on a vector and dot the product, dot the result with the same vector as we started with, right? Just as we did for C. So let's check. Is E positive definite? Okay? Consider a vector just as we did before, epsilon m. Okay? And now form the product epsilon m dotted with E acting on epsilon m. From the definition that we have for E and that we've reproduced at the top of the slide, we know that this is epsilon m dot, well, we can pull the 1/2 outside, so we have epsilon m C epsilon m minus epsilon m dotted with isotropic tensor epsilon m. Now, this is the square of the original length of the vector. Here we have the square of the length of the deformed or stretched vector. After deformation, does the vector have to have a greater length than it had before deformation? Think about it. What we're asking is that if we have a vector scribed here, are we also considering deformations of the type where that vector has now been shrunk down a little? Yes, we are. Right? As a result, what this implies is that the square of the length of the deformed or stretched vector does not have to be greater than the length of the vector before deformation. Okay? So as a result, it implies that this product that we started considering okay, this thing can be less than 0. Okay? As a consequence, E is not necessarily positive definite. Okay? E is not positive definite. All right, we're going to take a break here and stop this segment.